rule. Use the chain rule. So the relation between these variables is that y is a function of x, x is a function of u. Therefore, by the chain rule, we have the following result. By chain rule, we know that y2 u1 y2 un minus 1 yn u1 yn un minus 1. This matrix, what we want is the determinant of this matrix. This matrix can be written by the multiplication of the Jacobian matrix for y which is respect to x, multiplying the Jacobian matrix of x which is respect to u. That is y2 x1 y2 xn yn x1 yn xn. Okay, multiplying the Jacobian matrix of x which is respect to u, x1 u1 x1 un minus 1 xn u1 xn un minus 1. Okay, so we have this matrix multiplication. If the right hand side are the multiplication of two square matrices, then the determinant is precisely the determinant of both matrices, the multiplication of the determinant of both matrices. Unfortunately, on the right hand side, this is n minus 1 rows and n column, and the second matrix is n row and n minus 1 column. The multiplication is n minus 1 by n minus 1. Okay, so to compute the multiplication of such two matrices, a factor matrix and a tall matrix. Okay, because the first matrix, the number of row is less than the number of column, while the second matrix, the number of row is greater than the number of column. So in linear algebra, we have a Cauchy-Binet formula. By Cauchy-Binet formula, to compute the determinant of the multiplication equals, you remove the i's column from the first matrix, then remove the i's row from the second matrix. Removing these two, removing the i's column from the first matrix and removing the i's rows in the second matrix, then both matrices become an n minus 1 by n minus 1 square matrix. Then you can compute their determinant, and the multiplication of this determinant is a number for I. But for I from 1 to n, adding all this multiplication, the result is the determinant of the multiplication matrix. That is, we have this result. This is sigma I from 1 to n y2 yn. Removing the i's column in the first matrix is precisely the Jacobian matrix of x1, which xi removed. Okay, removing the i's column from the first matrix means that xi is missing. So we express by xi which is ahead, and I write in red. Similarly, for the second matrix, you removing the i's rows That is, you will obtain the x1, but no xi. Xi is missing. Then xn, which is back to u1, un minus 1. Okay? This equality is using Cauchy-Bennett formula. As I said, the determinant, what we want to compute, the determinant of this matrix, the multiplication matrix, equal the sum of such numbers for every I from 1 to n. For any I in this range, you remove the ith column from the first matrix and remove the ith rows from the second matrix, then computing their determinant and taking multiplication, and this is the number for I, and summing this number from I to n. The result is the determinant of the multiplication matrix. Therefore, we have this equality. Okay. Now, this equality is precisely, the summing result is precisely the inner product of A with n tilde, right? The component of what? This number is the component of A, which is up to a sign -1 to the power I plus 1. This is the component of A. On the other hand, up to a sign, this is the component of n tilde. Here, this the last line in this page. The component of AI, and the component of n tilde are given here. So comparing these components, you will see that this sum is precisely the inner product of these two vector fields. Okay, so we have this equality. Positive or negative new one multiplying the norm of n equal a inner product with n tilde. Okay, this is our first proposition. Then we also compute a quantity very important to us. The quantity is the divergence of p tilde A. We need to compute this quantity. P tilde is a function defined on omega. A is also a vector field defined on omega. Because A is the Jacobian determinant of y with respect to x. A is a function of x. X belongs to omega. So A is a vector field defined over omega. Okay? Therefore, we want to compute this divergence, P tilde A. Now we compute the divergence in the next page. Our AI, we want to compute divergence of P tilde A. Here, we look at the AI. AI is the cofactor of y1 of this number. We denote it by yi1. That is the partial derivative of y1 with respect to xi in the Jacobian determinant of our map. That is the Jacobian determinant is the determinant of this matrix v prime x. V prime x is y1 to x1, y1 to xi, y1 to xn, y2 x1, y2 to xi, y2 to xn, yn to x1, yn to xi, yn to xn. Okay, this is our matrix. The cofactor of this element y1, which is the partial derivative of y1 with respect to xi. That is, you you remove these rows and remove this column, and then the remaining entries forms an n-1 by n-1 matrix. Its determinant multiplying with -1 I plus 1. That is the cofactor. But this is just the ith component of our A. Therefore, this is just AI. So this justifies our declaration that AI is the cofactor of this element in this matrix, or in the determinant of this matrix. That is our Jacobian matrix. So we have a result. We have not proved this yet, but we use it. There is an Hadamard identity. There is an Hadamard identity telling us that the divergence of this A, that is the sum of the partial derivative, is 0. We have not proved this. This Hadamard identity is just a result of our previous result in differential calculus, saying that DIJF equal DJIF. For missing partial derivative, you can switch the order. As a corollary of this result, by some algebraic computation, not difficult, you can prove the Hadamard identity, telling you that if a vector A is given in this way, its ith component is the cofactor of such a matrix, then the divergence of such a vector A is 0. Okay, we apply this result without proof. The proof is not difficult. Maybe I will provide you separately, but I will not cost time in this lecture. Okay, so we admit this result and apply it. And also we have, since AI is the cofactor, we also have this result. Expanding the Jacobian determinant by its first row, you will see that the sum I from 1 to n YJI AI. What's this? The result YJI. Here is J. Maybe I will write it again. YJI AI. What's this? If J is not 1, then Yij, if J is not equal to 1, is the jth row of the matrix. Then AI is the cofactor of the first row. Then you use the row multiplying the cofactor of the other row, then sum up. The result is 0. We learned in linear algebra. Okay. On the other hand, if J equal to 1, then Yi1 is the first row. The first row, the element in the first row multiplying the corresponding cofactor, then summing up. The result is precisely this determinant. Okay, determinant can be expanded with respect to a row or a column. So we expanded this determinant with respect to the first row or the jth row. You will see that if J is 1, then the result is the Jacobian determinant itself. Otherwise, it's 0. So this tells us that this summation equal delta J1. The determinant, that is our Jacobian determinant. Delta J1 is the Kronecker delta. If J is 1, then delta J1 is 1. If J is not 1, the delta J1 is 0. Okay, so we use the very convenient Kronecker delta to denote this result. Then with this at hand, we can compute our divergence. We are devoting to compute this divergence in this page.